So, the seminar will be in English, so I start in English for the presentation first. So I'm very pleased to welcome Liam Connor. I hope I say it well. Enough. So he's from the University of Amsterdam. He's working at the Anton van Kook Institute for Astronomy. He did his PhD in Toronto, at the University of Toronto. He's mainly working on fast radio burst, our main science topic. And very shortly on the instrumentation, when he was a PhD, he worked on the CHIME project.
Yes.
And now the ALERT project, which is a collaboration between LOFAR and Apertif to detect fast radio bursts and pulsars. So I'll let you give your presentation, and then for 1 hour, and then we'll have a few questions after that.
Perfect. Thank you very much. Thanks for hosting me. Sorry that I was almost late. We had some train troubles on the way down from Amsterdam. So yeah, today I'm going to be pinballing back and forth between artificial intelligence and machine learning and the subject to which we've been applying that in the Netherlands, namely fast radio bursts. So here's a very minimalist outline. I'll first talk about AI and its history in astronomy. I'll then talk about fast radio bursts and the way we're trying to detect them with the Apertif instrument on Westerbork. I'll then talk specifically about this machine learning pipeline I've built using tools from deep learning. And then I'll talk about future prospects for kind of more ambitious real-time machine learning on radio telescopes. If you don't like minimalist outlines, here's a maximalist one. This is just a word cloud that was taken from a paper I published a couple years ago on this subject. This gives you an idea of what I'll be talking about today. FRBs, convolutional neural networks, FRB candidates, classification, these sorts of things. And by the way, please stop me if you have any questions about either the FRBs themselves or the machine learning. So just to make sure we're on the same page and to say the vernacular up front, within the sort of concentric circles of artificial intelligence, one subset is machine learning, which has been very successful over the past few decades. And this aims to have computers learn on their own without being explicitly programmed to do various tasks, such as classification, prediction, even new data generation. Within machine learning, there's a subset of tools called representation learning, where rather than having a human scientist, an expert, engineer the features by hand, you actually have the model try to learn the relevant or the salient features from the data on its own. And the most successful subset of representation learning is deep learning, which you've probably heard about. Even if you haven't used it, it's had this sort of explosion since the early 2010s. And deep learning really refers to the application of neural networks with many layers. And this has had sort of quantum leaps in everything from self-driving cars to medical imaging to astronomy, natural language processing, translation. All of these things have been aided by this deep learning revolution. So I'll contend that, I'll say at the end of this talk that I think there's a lot of perhaps low-hanging fruit in astronomy and machine learning, where we haven't really caught up to the literature yet. That being said, there is a long history of using AI in astronomy. In the 1980s, principal component analysis was used for galaxy morphology. In the 90s, things like decision trees were introduced. In the 2000s, these decision trees were combined to form what are called random forests. Artificial neural networks were used, SVMs, a support vector machine. And then in the 2010s, astronomers really started to take advantage of both big data and the advances in model building and machine learning. So this is when we started to use deep neural networks, random forests, and this was done for real-time transient surveys in the optical, strong lensing, exoplanet discovery, photo-Zs, and gravitational wave detection. And it's a big question, the extent to which machine learning will be central, or what form it will take in big data astronomy in the 2020s. but it's very hard to imagine machine learning not having a fairly central role. If you want to see a review of all the ways that machine learning has been used in astronomy, Fluke and Jacobs is useful. This was from a few months ago. Okay, so fast radio bursts. Maybe just put up your hand if you've been in a FRB talk in the last year. Okay, so maybe half of the people. Yeah, so fast radio bursts, we've known about these for roughly 1 decade. These are mysterious bursts of energy at radio wavelengths. They last for about 1 millisecond. The first was discovered in 2007 by Duncan Lorimer, but there was a sort of FRB winter after that where for 6 years no new FRB was detected. And so people kind of became suspicious that maybe these were terrestrial interference or something. But then in 2013 and beyond, we started detecting more and more of these with different telescopes around the world. And now several are actually localized to host galaxies at cosmological distances. So they're interesting for a few reasons. One is that because of the distance scale, they have to be extremely energetic. So even though phenomenologically they look like radio pulsars, they're 10 to 15 orders of magnitude more energetic than typical radio pulsars in our own galaxy. And they seem to be relatively common. There are thousands across the sky each day, above roughly a Jansky. And as we dig deeper into the noise with more sensitive instrument, and when we start looking for even narrower bursts, say microsecond FRBs, I suspect that there are going to be tens or maybe hundreds of thousands across the sky each day. So the reason we know, or the reason we suspected at the beginning that they're far away, is because of this large dispersion sweep. So as radio waves travel through ionized plasma in the universe, low frequencies travel slightly slower than higher frequencies. And if there's a lot of plasma in the way, then you can get this really enormous dispersion delay. Now, the reason we thought they were at cosmological distances, basically as soon as they were observed, is because the amount of delay you would expect at these frequencies from the Milky Way is only roughly that much. Add on the galactic halo, maybe up to 100 kiloparsecs, and you can get that much delay. So to get these enormous dispersion sweeps, you either need the FRB to be living in a very, very dense plasma region, say a supernova remnant, or the sweep has to come from the IGM itself, from the intergalactic medium. And because the intergalactic medium is so much more diffuse than these other media, this would correspond to maybe gigaparsecs scales. And this just puts into perspective how FRBs really are outliers compared to other similar looking sources from our own galaxy. The blue dots here are pulsars as a function of galactic latitude. So this is the amount of dispersion sweep, the DM. And this looks like what you'd expect from objects that live in the plane. Whereas FRBs really come in at uniform random galactic latitudes, and they have these enormous dispersion measures. This is another way of looking at the phase space of radio transients and radio sources in the sky. The sort of gray region, which corresponds to maybe slowly varying transients or longer sources, which are not that luminous, are coherent, thermal, maybe H2 regions, for example. Whereas the blue region, which are high luminosity and short duration of time, correspond to coherent emission. So this includes pulsars and, of course, fast radio bursts. I mentioned that FRBs are fairly common. So another way to look at all the things that flicker in the night sky at radio wavelengths is you can draw a luminosity function. So on the y-axis here, I have number of bursts per year per cubic megaparsec. And this is sort of a back of the envelope. You should trust these scalings to maybe 2 orders of magnitude, but it shouldn't really matter. Pulsars have a luminosity function that looks like this. There's a tail, a power law tail of giant pulses that some pulsars exhibit, which are much brighter, but a little bit less common. And then there are short bursts from planets like Jupiter and from the sun, of course, which are much more common, but much lower in energy. And then there are fast radio bursts. So, of course, FRBs are much less common per cubic megaparsec than our pulsars or short duration bursts from stars. But they're also much, much more energetic, and they're actually a lot more common than things like binary neutron star mergers. So you can't really explain the FRB phenomenon just by invoking, say, one FRB per one short GRB or one long GRB even. Yeah.
Can we interrupt?
Yes, please.
Yes. This is just to say that when you give the luminosity, you assume an isotropic emission, right? And maybe you are aware that at least one mechanism that was proposed in the literature has an amplification factor of 10 to the 10 approximately, due to the motion of a source in a pulsar wind. And this brings the energy related to FRB to typical pulsar energy.
Yeah, this is a good point. The isotropy assumption is sort of a big assumption here. Yeah. But of course, as you turn down the isotropy and you turn up the anisotropy, you have a small beaming fraction. Now you need that many more progenitors.
Yeah, absolutely.
Yeah. And I would just note that there's this gap between giant pulses, if you trust these luminosities, between giant pulses and FRBs, and we're not quite sure what lives there. We don't know if there's some continuous spectrum between, say, Crab giant pulses and fast radio bursts, or if there's some sort of a valley. As with GRBs, there are lots and lots of theories to try to explain where fast radio bursts come from. It used to be a joke, dare I say, a big cliche in FRB talks, to point out that there were more theories than actual detected events, and that was true, I think, until last year. This is a small subset of them that Tony Pira has put together. One big differentiating factor between two types of theories is that some are cataclysmic, which is to say the progenitor is destroyed, and some are non-cataclysmic, which means they might be expected to repeat. And you'll see up in the blue there, I'm guilty of a couple of these. I published a couple of papers suggesting that FRBs are probably young neutron stars and in dense magneto-ionic environments, whether near galactic nuclei or in supernova remnants. But we've detected a lot more FRBs now, and it's no longer true that there are more theories than events. So there are a number of different efforts around the world. Baptiste mentioned one in my introduction. CHIME is, of course, has been very successful at detecting fast radio bursts recently. There's ASCAP in Australia. We in the Netherlands have Aperitif, which is an upgrade to the Westerbork synthesis radio telescope. So the 12 dishes in Westerbork have been upgraded with these phased array feeds, which basically just means you put a little radio camera at the focal box of the telescope and you increase the field of view by a factor of roughly 30. So this makes it a much better FRB finder and a much better survey instrument. Here's a little flyby. If you're not familiar with Westerbork or you don't do radio interferometry, this is a redundant east-west array with the longest baseline of about 1.4 kilometers. And what that means is you have very good localization, you have very good spatial resolution in one direction, but your spatial resolution in the orthogonal direction is limited by the size of the dish. So these are 25-meter dishes. At our frequencies, this means you get this very long, kind of hot dog-like localization region, which is 20 arc seconds in one direction and about 20 arc minutes in the other direction. We sample the electric field at a pretty enormous rate, so each of those phased array feeds altogether samples the electric field at a rate that produces 7 terabits per second, so that's actually larger than the internet in the Netherlands. And those 7 terabits per second must be converted into a single bit effectively, where you say there is or there is not a fast radio burst in this chunk of data. And this has to happen in real time because, of course, we cannot save the disk, all this data, and we want to send triggers to nearby telescopes like LOFAR and telescopes in other wavelengths as well. So to this end, we have this 40-node GPU cluster. Each of the nodes has 4 GPUs, 4 1080 Ti's in them. And like I mentioned, we want to send out real-time triggers because of the dispersive delay, because of the large dispersion measure of fast radio bursts. We get about 1 or 2 minutes of delay time between L-band, 1400 megahertz, where we detect the FRB at aperitif, and LOFAR, which observes between 100 and 200 megahertz in the high band array. So that's actually quite a bit of time. We can definitely keep up with this latency, but everything still has to be done in real time, and we can't trigger LOFAR many more times than once or twice per day. Because we save voltage data, and we have these what are called transient buffer boards, which take a long time to read out. So we have to be very precise, and we have to be very accurate in when we actually send a trigger to LOFAR. Now, if you just do the kind of dumb thing and you have your dedispersion pipeline look for FRBs in the raw data. So basically, because you don't know when the FRB arrives and you don't know how much DM it has, you have to try every trial DM, every physically reasonable trial DM, and you have to look for peaks at every timestamp after summing across frequency. This is a very computationally expensive procedure, which is why we have that 40-node GPU cluster, and you end up with huge numbers of false positives. So this is a needle in the haystack problem, but in this case the needle is an FRB, and the haystack is this huge phase space with non-Gaussian noise, which is multidimensional. And the way we used to search this phase space is, because we'd have much lower data rates, a graduate student or a postdoc would look through by eye all of the candidate plots. This is what I did during my PhD. And having been told that FRBs kind of look like single pulses from pulsars, and RFI, radio frequency interference, kind of looks like this, you go through and you act as the biological neural network to decide which is real, which is a false positive. But as I've kind of emphasized, the data rates are so huge now, and it has to be done in real time, and this problem is intractable, which means sifting through candidates really has to be automated. So when I first started playing around with this problem, I used some more conventional, sort of classical machine learning algorithms, like support vector machines and random forests. But after digging around a little bit more and considering the fact that the main data input that we use to decide if an FRB is real or not is this sort of two-dimensional dynamic spectrum. This is frequency versus time, and the amplitude of the array is intensity after removing that dispersive sweep. It seemed like a pretty obvious route to just use a convolutional neural network, a 2D CNN. So this is the thing that's been so valuable for machine learning, for deep learning image recognition. If you're not familiar with convolutional neural networks, the input is this FRB dynamic spectrum in my case. And then there are these two kind of basic categories for the architecture of the neural network. One is the feature extraction components. This is highlighted in green. And in red, the sort of classification layers. So the way this works is a set number of convolutional kernels, each of which is slightly different, is applied to the original image. At the next layer, there's a layer called pooling, which is basically just a coarse average in small boxes. So sometimes people use what's called max pooling, which means in any little region of a 2x2 box, you take the maximum value there. You then apply more kernels, and depending on how many convolutional layers you require or can fit on your GPU, this eventually gets to the classification layers, where after the feature extraction has been done by the convolutional layers, it can try to decide which category the input data belongs to. So in my case, this is a fairly lightweight and simple binary classifier. Okay, so we have a probability as an output of the source being a true FRB or noise or radio frequency interference. This is an example. Here's an example of some of the kernels that are applied to the image. So this is sort of an edge. You can use an edge detector, this sharpening kernel, and it shows you on the right side. This is taken from Wikipedia, roughly what each of these operations does to the input image. But when a human expert is looking through these plots, like the graduate student I was, and the way people used to do this, you're actually looking at multiple input data products. So you're not just looking at the frequency time plot, but you're also looking at the pulse profile in time, and you're also looking at the DM time plot. So if you imagine the FRB showing up with a single sweep, it should arrive at a single time and with a single well-defined DM, which means in this space you should have sort of an island of signal. Right? It shouldn't be too spread out in DM time space. And so what you can do is you can build models for each of these inputs and then get a probability for each of the outputs, or you can kind of combine them into a single neural network such that each one has its own feature extraction layer, because of course the data are projected into a different space, and so they're going to have different relevant features. So it can learn the features independently, but then you can concatenate into single fully connected layers. And if you train this whole thing together, you get a single output probability. Keeping in mind this was for one candidate, just with the data projected into different spaces. So you get a single output probability, and the neural network should in principle learn that, okay, the DM time plot looks like this, but the pulse profile looks slightly off, then maybe the probability is not very high of it being real. One issue, of course, for us is that one of the great successes of deep learning in the last 10 years is the availability of large computing clusters and GPUs, but also the availability of huge training sets. And we have the former, but we do not have the latter, because at the time when I started this, I think we only had 24 FRBs detected. So to get around this problem, as a training set, I used roughly 30,000 hand-labeled triggers. So because we had done an early pilot project, and because I had been working on Chime already, we had huge numbers of false positive candidates that somebody, mostly me, I guess, had labeled as being RFI or noise fluctuations. As the sort of true positive component of the training set, we simulated FRBs, injected them into real noisy data from a telescope, and we used a large collection of giant pulses from pulsars in our galaxy. Another nice thing about this sort of hierarchical tree neural network that I described, where everything is combined, is that you can remove or you can add on new branches to this tree somewhat arbitrarily. So if you find that the dynamic spectrum is doing well enough, then you can just use that. If you think there's some useful information in the multi-beam detection, then you can start using that too. So here we can incorporate the multi-beam information by training a neural network to learn that if two beams that are separated by, say, 7 degrees on the sky go off with high signal to noise, then this is probably a terrestrial source. This is probably radio frequency interference. Because if it were in the far field, if it were a real astronomical transient, then really it should be strong in one beam and maybe a little bit less strong in adjacent beams. But you shouldn't have non-adjacent beams or all of them going off. So the neural network can learn which combinations are allowed to go off at the same time. And you can just sort of lock this on.
Can I ask a question? Yeah. The dispersion measure, you compute it on the fly also? Or?
Yes. Yeah. So that's actually where most of the compute goes of that GPU cluster, is just by doing this brute force search over, I think, 3,000 dispersion measures for every arrival time. And then it has this huge list of candidates, and it says, this is the DM, this is the arrival time, tell us if it's real. So the way this works in practice is that huge list of candidates is produced by the GPU cluster, We do some fairly simple clustering to say, well, if these two triggers are separated by a millisecond and have the same DM, well, I'll just take the highest signal to noise one, and that's a candidate. And then those get sent to my classifier, which was written in Keras, Python with a TensorFlow backend. This runs on the GPUs, and then we get an email with everything that passed the probability threshold that we can set beforehand. So in this case, I think the probability threshold was only 0.5. This is a pulsar in our own galaxy, 1933. Or maybe it's the Crab, I can't quite see. Oh yeah, it's the Crab, 0531. So these are all giant pulses from the Crab, and this is a good way of knowing that the classifier is working. But sometimes when you're looking at a blank field, you get lucky and you find an actual fast radio burst. So this is another email that we received not long after that observation I just showed, where nothing except for this one, what seems to be a real event, actually made it through the classifier. You can see there's a slight difference between these figures and this figure, in that this has a little red box around it. And that's because it has a dispersion measure that's larger than what you would expect from the galaxy in that direction. So this one happens to have a DM of about 600. So this is good. Aperitif, the FRB survey on Aperitif seems to be working. These are the first new FRBs discovered in Europe, if that means anything. But we had a relatively high detection rate. We're not as high as CHIME, but we seem to be detecting them once every 4 or 5 days on Sky, which I think would make us number 2 in detection rate in the world. And we're at a different frequency from CHIME, which is useful extra information. We're at 1400 megahertz, and they're between 400 and 800. Okay, so it's worth asking what next. I mean, what I've just described to you was basically just solving the sort of real bogus problem, which was solved maybe a couple of years before us in optical transient astronomy, where you say, is this junk or is this worth looking at? But you could probably be a lot more ambitious about this. And certainly for next generation radio instruments and next generation transient surveys, we're going to have to be. So it's worth just kind of surveying what's been done in the last few years in different subfields of astronomy. In solar astronomy, there seems to have been a decent amount of work on flare classification and predicting solar flares. I suspect there are people in this room who could tell us about the efficacy of these efforts. I don't actually know how good they are at predicting solar flares. But Liu et al., for example, in 2019, used these so-called LSTMs, long short-term memory recurrent neural networks, which are good for natural language processing and language generation, basically analyzing complex 1D time streams. In gravitational lensing, surveys like LSST and Euclid are going to produce maybe 2 or more orders of magnitude more galaxy and quasar-galaxy strong lensing objects. And so searching for 10 to the 4 or 10 to the 5 is going to have, of these sorts of sources is going to have to be automated. And there was a blind search for strong lensing challenge in Metcalf et al. 2019. Also, the lens mass distribution modeling is very difficult. If you actually observe one of these strong lensing sources, trying to figure out exactly what the dark matter configuration and density profile of the lens is very important for doing cosmology, but it's also very difficult. And so people have started using deep neural networks for this. In cosmology, there have been other similar efforts. You can kind of divide these into 2 categories. One is speeding up slow processes, and the other is trying to attain superhuman accuracy or precision or predictivity or something like that. So the Wiener net is actually, this is a really cool paper if you want to check it out. It's by 2 scientists at Perimeter Institute in Canada. And they trained a neural network to basically imitate the Wiener filter, which is essential in all of CMB analysis, and is actually a time bottleneck for generating simulated maps. GANs have been really useful for large-scale structure simulations, and deep neural networks have been applied to weak lensing as well. In transient detection, as I mentioned, the optical community was on the ball fairly quickly. And this was true at Catalina. Of course, ZTF and Pan-STARRS have needed to solve the real bogus problem, but more ambitiously have tried recently to do early supernovae light curve classification. In the radio, what I've just described is basically a false positive rejection model. So we're not saying this is this sort of FRB, it's likely to repeat. It's nothing beyond saying that it's not junk and we should preserve it. Deep learning and machine learning in general has been applied for several years in pulsar classification. They have a similar problem where huge numbers of candidates are produced when you do a pulsar search. And so towards the end of this project, I started thinking, well, how could we use these neural networks in a more ambitious way? How could we replace more of the real-time pipeline with the neural network, since it seems to be so effective and since it can be run so quickly on a GPU? And so one thing you might do is, rather than taking in the raw data and searching it over every single dispersion measure, this sort of brute force method that I mentioned before, maybe you could just feed the raw data directly to a massive neural network and have it pick out the FRBs on its own. So this is quite different. This is quite a different scope problem than the one I described before. When I showed you those convolutional neural networks, I was giving it a little stamp, basically, 64 by 64 pixel time frequency array, which can be processed very, very quickly. But if you're using raw data, this would be maybe 1,000 or 5,000 frequency channels in the one direction, and maybe 10,000 samples in the other direction. So it would require a much larger neural network, and it might end up being kind of slow. You need the translational invariance of a CNN because you don't know when this FRB is going to arrive. And it's also very different in that, even though you can probably see the sweep here, for most FRBs, the signal to noise per pixel in this raw data is going to be much less than 1. And so you're not going to be able to see it by eye, which means you need a neural network which can find this very low signal to noise event and dig it out and reliably flag it and tell you where it is in the data. So the first thing you might do is just do a very simple big O scaling and try to figure out the computational complexity of this. So could you even keep up? And it's not that hard to do because these neural networks are basically just a bunch of matrix multiplications. Even the convolutional layers, so going back to this 2D CNN that I had before, the convolutions on a GPU are lowered to matrix multiplies, which is, of course, what GPUs were designed to do. And these fully connected, the classification layers, are also just matrix multiplies. And at each step, you know the size of the matrix, and so you can calculate roughly the computational complexity. Well, convolution is very, very slow if you do it in the brute force way. If you have a length n vector convolved with itself, that's an n squared operation. If you have an n by n grid, this is n to the fourth. So you end up with a scaling that's n to the 2d, where d is the number of dimensions of the input convolved matrix. But that's different from what we're doing here. What I'm suggesting here is a large input array, n by m, convolved with a very, very small sort of m by m, often 3 by 3 convolutional kernel. And GPUs are really good at this, particularly with the new tensor cores, if you've heard about these. These are accelerated hardware that companies like NVIDIA put out basically just for deep learning purposes. And so I won't bore you with the details any further, but it turns out that for reasonable assumptions about the size of the neural network you're using, you can be faster than this brute force method that I was describing before. And when I included this in a section of our paper, we were kind of skeptical, and we said, yeah, this is an interesting path to go down. It may not be prohibitively computationally expensive, but you might as well just stick with the brute force method. But within a few months, this group at Berkeley, led by a graduate student, Jerry Zhang, had actually done this on real data, which was really cool to see.
Just one question. The complexity you're talking about right now is using the network or training it?
Oh, sorry, just using it. I should have clarified that. Yeah, training is still going to be very slow. But when you're actually trying to find the signal in real time, all you require is a single pass through this network. So you train it offline, you have all the weights and the biases saved, and then you apply that, which is just a bunch of matmals. So this group this group led by Jerry Zhang at Berkeley had data in which they suspected there were, or maybe they knew already that there were repeat FRBs from the first repeating source, 121102. And they trained it on simulated data, I believe, and they didn't do any dedispersion, they didn't use any of the traditional methods, they just applied a neural network to the data directly, and they recovered a whole bunch of new bursts from this source, which was exciting. There are a couple caveats though. One is that this is at high frequencies, which means, so this is between 4 and 8 gigahertz, which means the dispersive sweep is not as severe, which means you can add frequency channels up and you can get up to those more reasonable levels of signal to noise per pixel that I mentioned before. So the classifier is not so different from a human inspector. If you and I can see it by eye here, then you could probably train a CNN to find it. And this would be quite different, I think, if you were searching for FRBs in this method with chime at lower frequencies where the signal is spread out over 30 or 40 seconds. So that's a caveat. I alluded to these tensor cores. So there are these new there's lots of new accelerated hardware inspired by the demand for fast deep learning modules. So the best known and probably the most effective one are these tensor cores. And right now it's the Turing tensor cores on NVIDIA's GPUs. They seem to have sped up these matrix multiply accumulates greatly. And so that not only speeds up classification, but of course it speeds up training of deep learning models as well, which can often be very slow. And looking forward, we in the Netherlands have this consortium that was formed in the last year called Cortex, the Center for Optimal Real-Time Machine Studies of the Explosive Universe. And we found out about 6 months ago that we won this €5 million grant led by Yuri van Leeuwen, my current supervisor. And this is a multidisciplinary approach to applying accelerated machine learning to astronomy across a whole bunch of different fields. So we go from sort of fundamental machine learning research, mathematicians and statisticians, to astronomers, to programmers, to try to solve problems in gravitational waves, radio afterglows, FRB detection, LIGO detections, and the discovery of new, previously unknown transients. But yeah, as I mentioned before, I think we've done a reasonably good job so far at applying machine learning to astronomy, but there's a lot of low-hanging fruit. If somebody ends up spending 6 months or even just a year of becoming as familiar with the machine learning literature as, say, an ML master's student, you can end up doing really remarkable things, I think, in radio astronomy. For example, fast RFI mitigation, new techniques in map making and calibration, and of course, as I've been talking about today, transient detection. There are, of course, lots of issues with just applying these big, complex models to your scientific problem, namely the interpretability problem. Neural networks are often accused of being black boxes, which they are. And there are techniques, there's a whole subfield in machine learning research dedicated to interpretation and trying to understand exactly what the neural network is finding salient or interesting or relevant about your data. But it's still a difficult problem. And because we're trying to understand nature, we need to understand how our tools are analyzing our data, or in the case of simulations, producing new data. Another useful tool, I think, is going to be data challenges, benchmarking. I've been leading this thing in the Netherlands, which is an international effort to standardize FRB detection. I mentioned that there's CHIME in Canada, and there's the DSA in the United States, and there's ASCAP in Australia, and there's Aperitif in the Netherlands. And each one of those uses a different computing cluster, and they use different algorithms for finding FRBs written in different programming languages. And so we're hosting this thing that we've started calling the FRB Olympics, where everybody submits their code. We have maybe 100,000 FRBs injected into data, and each of them tries to find them. And we have a code comparison in this way. This will be really useful, I think, for machine learning techniques. And of course, with sites like Kaggle and OpenML, this already happens fairly regularly. There are also new techniques that will be interesting specifically for radio transient astronomy, where the data rates are so enormous. For example, compression and compactification. If you imagine training a huge model offline, which does really well but is very bulky and cumbersome, there are certain techniques like pruning where you can kind of approximate that huge neural network with a smaller neural network that does almost as good of a job at classification, for example. So this will be interesting to pursue, as well as the sorts of accelerated hardware that's now available, which we should be taking advantage of. And that's all I have to say, so thanks very much for listening.
So, any questions for Ryan?
You mentioned it at least twice. It seems that for now, what you're doing when you're preparing your learning sample is using models to generate the true events. I don't know anything about the theory of FRBs and what's in the models, but that's something that would be a little bit. I mean, how much do you trust the model? Do you think that there is no hidden variability that could? Maybe you could classify something wrong when it's a real one, just because the special features of this one are not in the models.
Yeah.
So
that's definitely something to be afraid of when anytime you're simulating data for your training set. In the case of FRBs, we thought we could get away with it because it's the false positives, the RFI, which is so unpredictable. So the false positive in your training set look like this crazy zoo of events that you could never simulate. Whereas FRBs can probably be simulated with 6 or 7 parameters. A width, how much spectral variation is there, how much deviation do you have from this lambda squared sweep. FRBs themselves appear to be sort of delta functions with attitude, if you see what I mean. And so when we simulate them, we do try to make them as ratty as possible. We try to give them ugly frequency spectra. I'll show you an example. Like this one in the top right, or this one in the bottom right, which is scattered, with the hopes that if FRBs are uglier than have been found before, they will still fall under this umbrella of that the model has been trained on. But I agree, this is something to consider for sure.
Do you have hope that? I mean, what's the rate at which the true detections? I mean, the new FRBs in the sky. Do you enrich your learning sample with those true events?
True events. Yeah. Yeah. So the plan is to, in an automated way, update the training set periodically. When CHIME starts publishing their FRBs, that will be a really nice large bundle to include in the training set. At the moment, I haven't yet. It's just things like crab giant pulses and single pulses from pulsars in the galaxy, plus these simulated events.
About the repeating FRBs, have you a mechanism to find the same directions on FRBs? Because you are expecting some. How many have you? So maybe you can include that in machine learning, that they must come from the same direction.
Yeah, that's a really good point. So there are now 20, as of 2 days ago, I guess, 20 known published repeating fast radio bursts. And indeed, if you're searching in that, if you're looking in that direction where an FRB is known to have been discovered before, you should have a lower threshold, either in probability or signal to noise, for candidates in that region of phase space. And we kind of do that. We do sort of an ad hoc search where we say if we see any candidate, even if it's 5 sigma in this direction with that dispersion measure, save the data, look at it by eye, or feed it to the model with a lower probability threshold.
I have a question on so your algorithm that you apply to the raw data.
Mm-hmm.
So it's still a yes or no algorithm, or do you derive also the dispersion measure so that you can automatically guess when it could the event would arrive at a lower frequency, for instance?
That's a really good point. So the way, keep in mind when I thought about this, it was purely theoretical and trying to get a complexity scaling. When the Berkeley group actually did it, I don't think the neural network actually output a dispersion measure.
So you still have to compute it at some point. Yeah. But it's on the lower.
But you have a much smaller chunk of data if it's been flagged. It's a good point though. That would be.
If you want to automate, to have an automated pipeline that drives even to other telescopes, you have at some point to be able to derive that.
That's a really good point.
Yeah.
I mean, in principle, like if the model were reliable enough that for 99.9% of the data it says there's nothing, but for 0.1% of the data it says there's an FRB there, then you could just do brute force dispersion very, very quickly and figure out what the DM is. That wouldn't take more than a fraction of a second. But yeah, it's a good point.
Yeah, maybe a stupid question, but how can it be adapted to directly search for patterns on time series, not on dynamic spectra? Will it be, the signal is less sparse than in the Fourier plane, but will it be adaptable to, let's say, a transient forward time series or something like this? That is a wideband, not generalized.
Yeah, so we effectively do that with a one-dimensional CNN, a one-dimensional convolutional neural network with the pulse profile.
Yeah.
But this is already having found the dispersion measure, the preferred dispersion measure, adding over frequency. And so you have this collapsed time series effectively.
Yeah, but even to find, to search for dispersed signal in the time series. So let's say to have some sort okay, I'm not talking about neural networks, but if you have a bank of generated time rates, for example, that's how they do it for gravitational wave. Could it be possible to have some kind of training that will search in sufficiently large windows to capture some signal that is dispersed, but you will see that as a chirp, yes, in the time series? Will it be even faster than trying to compute, to channelize and compute dynamic spectra?
Oh, that's an interesting question. So you're saying on raw voltage time stream data?
Yeah.
Yes, raw time stream.
Truly raw. I mean, the difference, of course, between a impulsive radio signal and a gravitational wave is that the impulsive radio signal is actually just an increase in noise at that time. You don't have a priori physically known template, right? Unless you know the motion of the electron.
It's an increasing frequency chirp. So it's almost the same. I mean, it's not like okay, I see your point, but the detection method is agnostic to whatever signal is inside. So if you are able to detect an increasing frequency chirp, you can think of having a model-independent chirp detector that is looking like a pulsar chirp. I don't know.
That's an interesting question. I think more generally that people should start thinking about analysis of very high time resolution pre-channelized voltage time streams.
Yeah.
So for example, if you want to look for gravitational lensing of FRBs, which could end up being one of the most interesting applications, this will have to be done in the time series you're talking about.
Okay.
There it's a little bit easier because you're just correlating signal against itself and you're looking for peaks at various legs.
when you talk about compression in your last slide, that's what we call the compressed sampling or compressed sensing. So you find a representation of your data where you can remove the small SVD, the small. Well, you do an SVD and you remove the small eigenvalues. That's what you mean?
No, I'm actually talking about compression of the neural network itself rather than of the data. So imagine you have this great neural network with 50 hidden layers and like 12 different convolutional layers, and it works perfectly, but it's way too slow to use in a real-time transient survey. You can try to approximate it with a smaller network with, say, 4 convolutional layers and 3 fully connected layers.
And how would you decide on those, on some measure of the efficiency of one path? Or?
Yeah, it's a good question. I don't know much about these pruning methods and these compactification methods, but I think you would just apply both the large and the approximate neural network to the same data, and you would use the standard metrics, accuracy, precision, F1.
You mentioned that there are many theories for FRBs, so where there may be some kind of sources for FRBs. Do you have any plans for your detectors, not only to flag them, but to classify it?
Yeah,
maybe with even unsupervised learning, just for the neural network to tell you if there are different kinds in your.
It's an interesting idea, yeah, and I think, I mean, of course, this will only be possible once we have many dozens, or ideally hundreds or thousands of them. But already in that Chime paper from this week, which had 9 new repeating fast radio bursts, for some reason it seems like the repeating FRBs are much broader than the non-repeating ones. I don't know why that would be true, but this seems to, and this was found the first 8 or 9 repeating FRBs that they found. So already by eye, even with really dumb human clustering, you're saying, oh, this group is wide and this group is narrow. And so with smarter unsupervised learning, you might be able to separate into subgroups along less obvious axes, I suppose.
Okay, so if there is no other question, we can thank again Lion for. So we have the room booked for until 5 p.m. So if you want to stay and discuss with him, we're here. And for the people who are in Meudon, tomorrow we will be also in Meudon, so we can discuss. Okay, thank you.
Thank you.